The Kuiper Belt, once defined primarily by Pluto, was the first major Kuiper Belt object, KBO, discovered. After Pluto's discovery, it wasn't until 60 years later that scientists observed another object in this region. However, this all changed on November 2, 2015, when the world witnessed a monumental photograph from space, marking the first detailed image of a Kuiper Belt object. Now, the James Webb Space Telescope has just delivered the sharpest image of the Kuiper Belt ever, revealing features no one expected. Located beyond Neptune's orbit, the Kuiper Belt forms a cold, donut-shaped zone at the outer edges of our solar system. Its discovery has provided new insights into the solar system's structure. Initially, the shape of the Kuiper Belt was the main point of interest. But over time, it became clear that this region held even greater significance for our understanding of the solar system's evolution. The Kuiper Belt is named after astronomer Gerard Kuiper, whose early 20th century work predicted the existence of objects beyond Pluto. Though Kuiper did not directly discover the belt, his theories laid the groundwork for understanding this far-reaching part of the solar system. In 1951, Kuiper introduced the idea of objects beyond Pluto, but he did not predict the precise structure or characteristics of the region. Instead, his focus was on the possibility of distant bodies existing past Pluto. Though Kuiper's predictions did not fully match later findings, his work was instrumental in guiding future research. Initially, Pluto was considered the defining object of the Kuiper Belt. However, it has since been recognized that Neptune's orbit, not Pluto's, marks the inner boundary of the Kuiper Belt. The gravitational influence of Neptune has played a crucial role in shaping the dynamics of this region. While Kuiper's work laid the foundation for our understanding, the specifics of the Kuiper Belt's composition and its relation to objects beyond Pluto were uncovered later. In 1930, astronomer Clyde Tombaugh discovered Pluto, placing it in what we now know as the Kuiper Belt, making it the first confirmed object in this region. At the time, the understanding of the outer solar system was limited, and scientists did not expect a large population of icy bodies beyond Neptune. The prevailing model of the solar system was based on the inner rocky planets, the gas giants, and the outer frozen giants like Neptune. Pluto's discovery, despite its erratic orbit, led researchers to consider it a lone planet. However, it wasn't until 1992, 62 years later, that the second Kuiper Belt object was found, confirming that Pluto was not an isolated object but part of a much larger population of bodies in the outer solar system. As additional KBOs were discovered, it became clear that the Kuiper Belt was home to a diverse array of icy bodies, including dwarf planets, asteroids, and comets. The belt is believed to be a remnant of the early solar system, containing materials from about 4.6 billion years ago, which can offer clues about the conditions of the early solar system. The Kuiper Belt is vastly larger than the asteroid belt, which lies between Mars and Jupiter. The asteroid belt, mainly composed of rocky objects, is relatively sparse and contains a limited number of small to medium-sized bodies. In contrast, the Kuiper Belt is a much larger and more remote region, with a mass estimated to be 20 to 200 times greater than that of the asteroid belt. This makes it a more significant area in terms of both the number and mass of its objects. The Kuiper Belt is not just important because of its size, but also because it contains key objects that could provide insights into the formation and evolution of the solar system. Notably, Pluto, with a diameter of approximately 2,377 kilometers, is one of the most significant discoveries in the solar system. Discovered by Tombaugh in 1930, Pluto was initially classified as the 10th planet. However, in 2006, the International Astronomical Union redefined planetary criteria, reclassifying Pluto as a dwarf planet. Despite this change, Pluto's discovery remains a critical moment in the study of the outer solar system. Other notable KBOs include Haumea, Makemake, and Eris. Haumea, discovered in 2004 by a team led by Mike Brown, stands out due to its unique elongated shape, likely caused by its rapid rotation. This dwarf planet, measuring around 1,960 kilometers in diameter, has provided valuable information about the characteristics of KBOs. Another KBO, Makemake, discovered in 2005, is slightly smaller than Pluto but more massive, with a diameter of about 1,430 kilometers. Its surface is composed of methane, ethane, and tholins, making it one of the brightest objects in the Kuiper Belt. Eris, also discovered in 2005, is larger than Pluto, with a diameter of about 2,326 kilometers. Its discovery helped to reshape the concept of a planet and expanded our understanding of the diversity of objects in the Kuiper Belt. These discoveries have provided essential insights into the composition and structure of the Kuiper Belt, shedding light on the early solar system. Without these objects, much of our knowledge about this distant region would remain obscure. Many people confuse the Kuiper Belt with the Oort cloud, but they are distinct. The Kuiper Belt is more densely populated with objects and is known for being a source of short-period comets, those with shorter orbital periods. In contrast, the Oort cloud is a more distant spherical region that surrounds the entire solar system, extending potentially as far as 20,000 astronomical units from the Sun. While the Oort cloud is thought to be a reservoir of long-period comets, the Kuiper Belt contains many more objects that influence the dynamics of our solar system. The Kuiper Belt and the Oort cloud are regions in our solar system known for containing frozen bodies, often referred to as dirty snowballs. These regions are linked to the long-period comets, which are characterized by highly elliptical orbits that bring them closer to the Sun. While both the Kuiper Belt and the Oort cloud are similar in that they serve as reservoirs for icy objects, they differ in location and shape. Nevertheless, both are considered potential sources of comets. The objects within these areas consist of ice, dust, and volatile compounds that become visible when they approach the Sun, as the solar wind causes them to develop bright comas and tails. One of the surprising aspects of the Kuiper Belt is the amount of material it once held. What we observe today may only be a small fraction of its original mass. The current objects are remnants, with much of the original material having dissipated over time. This isn't unusual, and it ties back to a theoretical model called the NICE model, which suggests that dramatic orbital changes occurred in the outer solar system. Specifically, the model proposes that the large outer planets, Jupiter, Saturn, Uranus, and Neptune, did not always occupy their current orbits. Instead, these planets underwent significant orbital migrations, leading to interactions that reshaped the outer solar system. According to this model, the migration of the gas giants likely caused the loss of a significant amount of material in the Kuiper Belt. Estimates suggest that the mass originally contained in the Kuiper Belt may have been 7 to 10 times that of Earth, but gravitational interactions with the large planets caused much of this material to be lost, ejected, or moved to different areas. As a result, the Kuiper Belt is now in a state of continual disruption, with collisions between objects leading to the formation of smaller Kuiper Belt objects, KBOs. Some of these KBOs may become comets, while others will not, but many are shattered, and the resulting debris can be blown away by the solar wind. The total mass of the Kuiper Belt today is thought to be only about 10% of Earth's mass, which makes it appear small. However, many of the objects in the Kuiper Belt have moons, smaller bodies that orbit around a larger object. This phenomenon is not limited to planets and extends to other objects in the Kuiper Belt as well. Additionally, some Kuiper Belt objects exist as binary systems, where two objects of nearly equal mass orbit a common center of mass, known as the barycenter. Some of these objects are in direct contact with one another, forming a contact binary shape, where the gravitational forces cause the objects to merge into a single form. NASA's Pioneer 10, launched on March 2, 1972, was one of the first spacecraft to venture near the Kuiper Belt. Initially designed to study Jupiter and its environment, Pioneer 10 became the first spacecraft to travel through the asteroid belt and later, in 1983, crossed into the Kuiper Belt region. Although it did not specifically study icy objects in the region, its mission was groundbreaking in that it provided valuable information about Jupiter and helped extend our understanding of the outer solar system. Subsequent missions, such as Voyager 2 and Cassini, further expanded our knowledge of the outer solar system. Voyager 2's flyby of Neptune's moon Triton in 1989 and Cassini's exploration of Saturn's moon Phoebe in 2000 contributed significant data about these moons, some of which are thought to have originated from the Kuiper Belt. The New Horizons spacecraft made history in 2015 by conducting the first flyby of Pluto, and during its journey, it imaged a Kuiper Belt object, KBO, known as 1994 JR1, providing crucial information about the composition and dynamics of KBOs. In 2014, the Hubble Space Telescope made significant contributions to our understanding of the Kuiper Belt by identifying 3 KBOs that could serve as potential targets for NASA's New Horizons mission. Hubble also discovered 2 frozen worlds within the Kuiper Belt near the edge of the solar system. These findings spurred further exploration and efforts to find a suitable target for New Horizons after its Pluto flyby. The Hubble Space Telescope's observations, dating back to 2003, have been instrumental in guiding our understanding of the Kuiper Belt and in locating objects of interest for study. With the advent of the James Webb Space Telescope, our ability to study the Kuiper Belt has been revolutionized. Using infrared technology, the James Webb Space Telescope can detect objects in the Kuiper Belt, where temperatures are extremely low. These objects emit infrared radiation, which the telescope can detect, providing detailed information about their composition and behavior. This capability has opened up new opportunities for exploring these distant regions of our solar system.